Okay, guys, today we're going to talk about the difference between discrete functions, or I should say discrete domains, and continuous. So typically when you draw a line and we have no word problem to go with it, they're all continuous. We connect all the points, we make a straight line, and that's continuous. Okay, that means that every interval in between works. So if you look at 0.9 on the graph for x, there is a point there, and 0.8 and 0.7 and everything in between, it all works. But if you're talking about a discrete function, we have to think about what the meaning is and what in real life is happening. So for instance, on a discrete function, let's say we're going to the movies, and I'll give you an XY table here. And we're going to say XY, but we're going to specifically tell you what the labels are for X and Y. So the labels are tickets to a movie, okay, and the cost. Okay, so let's say there's one ticket to a movie costs $10, and two costs 20, and three costs 30. So let's say that. Okay, so if I were to graph this, first of all, I'm not going to go into the negatives, and I'm going to just change these to tens so that we can just use the same graph. So one ticket costs $10, two costs 20, three costs 30, and so on. Now, discrete means that the ones in between don't work. So the values in between here for the domain. So can I have 1.5 tickets in the domain? And the truth is, I can't go to the movies and ask for 1.5 tickets. I either have to buy one or I have to buy two. I can't buy the intervals in between. So that would be called a discrete domain. And when we graph it, we do not connect the points. So it would just look like this. There's no straight line connecting it. Now, and you could put an arrow here because we can continue to go up and buy a new number of tickets. If we're talking about a continuous domain, an example for that would be, I'll take the X and the Y, but let's say we're talking about a side length of a rectangle and its perimeter. Sorry, it's a little bit messy here. I'm trying to squish it in. So let's say you have a side length of 10. And when the side length is 10, for example, the perimeter is, let's say one of the side lengths, let's say the perimeter is 60. Okay. And when the side length is 0, let's say that would be the smallest it would ever be. So if the side length was 0, the perimeter would be 40, for example. And if the side length is 20, it would be 80, and so on. And let's just say that's the pattern. Okay. You want to know if the intervals in between work. So I know you're thinking, well, 11 would work because you can have a side length of 11 and 12 and 13. So that's true. But I want you to be thinking about smaller than whole. So what about 10 and a half? Could you have a side length of 10 and a half, 10 and a quarter, 10 and an eighth, 10 and a 16th? And if you can have that, if you can break down your, oops, I'm sorry about that. If you can break down your, let me just fix that here. All right. If you can break down your domain into the smallest of portions and you can use all those intervals, then we would say that it is continuous. Why does it keep doing that on me? I'm sorry. All right. So in this case, this one would be continuous. And when I graphed it, let's say I have 0, 40, and I have 10, 60. We'll put the zeros on here. So we have 10, 60, and so on. When I graph it, I'm going to make a solid line because I know that all these intervals are still part of my solution group, and that's what it means to be continuous. So discrete, what I like to say is the intervals don't work. You don't connect the dots or the points. All right, so, sorry, this is really messy today. All right, so we're not going to connect the points. So the intervals, if the intervals don't work, you don't connect the points and it's discrete. All those D's go together. If you're talking about continuous, you do connect. So on continuous, you connect, and everything in between works. Wow, my pen's really giving me a hard time today. Okay, so that's the difference between discrete and continuous. That's as difficult as that gets.